Okay, welcome everyone. It's a great pleasure to have Jian-Hao Zhang as a speaker today. Jian-Hao got his PhD in physics in 2020 from Tsinghua University, and then he worked as a postdoc at the Chinese University of Hong Kong, Penn State University, and more recently at the University of Colorado Boulder. During the past years, Jian-Hao has worked on a wide range of topics, including high-temperature superconductivity and topological phases. But more notably, in the recent few years, Jian-Hao has spent a lot of energy developing the theory of mixed-state quantum phases. And I think because he is so productive in this direction, it's fair to consider him as one of the main players in this research direction. And we're happy to have him today to tell us about his work in this direction. Jian-Hao, please go ahead.
Well, thanks, Liu Jun, for the invitation and the very generous introduction. And today I'm going to talk about our recent very exciting developments of mixed-state quantum phases. You can see here I have a very large title of my today's talk. My talk is going to focus on the following two papers on arXiv. Okay. Before I talk about my today's ingredients, let me acknowledge my outstanding collaborators. They are Ruochen Ma is a postdoc in Chicago and gonna move to KITP at the end of this year. Leo is a graduate student in Perimeter. Zhen Bi is a faculty member of Penn State. Chong Wang is a faculty member of Perimeter, and Meng Cheng is a faculty member of Yale. Okay, as a physicist, we are always care about the properties of the physical systems. And the most ideal situation, as our expectation, is that we just leave the physical system away from our environment, just leave it isolated. That's our expectation, to keep all the physical properties uninfluenced by the interactions between the physical and the environments. But the real life is harsh. The coupling between the physical system and the environment is inevitable. But so for the physical reality, we should encounter all the interactions between physical and the ancilla spaces, including but not limited to the decoherence, dissipation, disorder, thermalization, etc. And we should note that the coupling between system and the environment could significantly change the behavior of the physical system we're talking about. So that's the motivation for us to investigate the physics in open quantum systems. Okay. Actually, in open quantum system, distinguished from the closed quantum system, the physical state in open quantum system is generally described by the mixed quantum states. And for mixed quantum state, a mathematical description is a density matrix rather than wave function for a pure state. And there are several representative examples for recent developments of the mixed quantum states. The first example is a quantum error correction codes under noise. The motivation for designing the quantum error correction code is that if you really want to transmit some quantum information from Alice to Bob, we should take care of the decoherence, etc., during the transmission. Okay, so we should design some algorithm to exclude the influence of the external decoherence of the system. That's the physical motivation behind the quantum error correction. So once we have an error correction code, we should talk about the performance of the error correction code in the noisy system. That's the physical motivation of this sort of mixed state. Another very exciting development for mixed state is that recently some sort of topological order has been proposed and prepared in the recently very rapidly developed quantum devices by measurement and feedback. We have a quantum device, but we cannot avoid the interactions between the quantum device and the environment. So for the real quantum device, we should also encounter the noisy system and consider the corresponding mixed states. Okay, that's the motivation for investigating the mixed states. Before we talk about the basic notions of mixed states, let's call back some pure state quantum phases and the corresponding basic notions. Well, when we talk about the quantum phases, we are actually talking about the equivalence relation. For example, if we consider two pure states, for example, psi1 and psi2, if we claim they are actually belongs to the same phase, it means that we can find a unitary evolution such that we can evolve psi2 to psi1 by unitary evolution. More precisely, the Hastings and Wen actually propose the quasi-adiabatic evolution of the pure state by the time evolution operator of local Hamiltonian. And there is a very elegant property for the pure state unitary evolution in terms of the equivalence relation, in the sense that if we can one-way evolve, then the two-way connectivity between the two pure states are automatically satisfied because of the unitarity of the time evolution. For example, as I formulated here, we can evolve psi2 to psi1 by unitary evolution u. Then we can automatically evolve psi1 back to psi2 by u Dagger. That's a very elegant property from the unitarity. And the equivalence relation between different pure states are based on the unitary evolution and the equivalence. Okay,
Question?
that's pretty, yes.
What is the meaning of this approximate equal sign?
Beg your pardon?
What's the here you that psi one is approximately equal to u psi two or
Well, actually, because you know, the difference between psi1 and psi2 can have some exponential tails. For example, if you consider the distance, for example, let's say the trace distance between psi1 and psi2, it can have an exponential tails of the evolution, of the quasi-local evolution.
wait. I think if you let the evolution to be generated by a quasi-local Hamiltonian, then there's no error at all.
You mean the quasi-local? If the
if
Hamiltonian is strictly
yeah,
local, then there.
yeah. So here you allow some error.
I allow some exponential error. Just
Exponential what?
exponential. Yeah, exponential to let me think. Uh, mm, uh, for example, well, I think the exponential for the length scale of the size of the system.
Uh-huh.
Yeah.
Okay. Then I have a
In the thermodynamic limit, it's strictly equal.
It well, if you take data as your definition and you assume H is local, then I don't think it has been proved that this equivalence relation is the same as the adiabatic connection of Hamiltonians.
Well, why?
It's a folklore that we often say so, but I don't think it has been proved.
Well, I think a more simple demonstration is that just if two states are connected by unitary circuit, then we claim they're equivalent.
Yeah, but these are all different definitions. A circuit is
Well, I
not
think
really the same as a time evolution of continuous time.
well if we choose psi1 and psi2 are the gapped Hamiltonian of oh 1 second, there's something. Oh yeah, okay. If we think psi1 and psi2 are some gapped Hamiltonian, gapped ground state of local Hamiltonian, let's say H1 and H2, and I think let's take HT such that if T equals to 0, HT equals to H1, if T equals to 1, HT equals to H2, then if we can actually prove that the time evolution operator is quasi-local, then we claim that the corresponding ground states are equivalent, I think.
Yeah, that's fine, that's fine. But here it seems you are requiring H to be local. Then that's a different
Yeah, it
definition.
should be local, and it should be local all the time.
But quasi-local is different from local.
Okay. Oh, if well,
I think as a general folklore, we believe these two classifications are the same, but I don't think it has been proved. In particular, I think even a more basic question, suppose I start from a product state and use a finite time evolution generated by a time-dependent local Hamiltonian to obtain another state. I don't think it has been proved that there's a local parent Hamiltonian that is gapped and has this state as its unique ground state.
Well, you mean there's no rigorous proof?
No, there's no rigorous proof. At least I
Oh,
don't.
sure. Yeah, but more precise, I think if we want to make the things without ambiguity, I think we can just focus on the unitary circuit and the corresponding equivalence.
Yeah, that's fine. That's fine. Mhm.
Yeah, yeah, good. So may I move on?
Sure.
Okay. Okay. After review the basic notions of the pure state and corresponding equivalence relation, let's move to the mixed state. Before we talk about the equivalence relation of different mixed states, let's talk about the evolution of the mixed state first. Because the mixed state is appeared in the open quantum system, so there is no unitarity at all. So when we talk about the evolution of the mixed state, the evolution of mixed state is generally described by local quantum channel that maps the density matrix to another density matrix. So before we talk about the equivalence relation, we should define the quantum channel first. There are three main steps of quantum channel. The first step is that we include all the environmental degrees of freedom into our consideration and towards an enlarged Hilbert space, including the system and ancilla. And with the system and ancilla altogether, we have an enlarged closed quantum system. Okay, as I said before, it's an enlarged closed quantum system. So the evolution of a closed quantum system is actually a unitary operator or unitary circuit. Then, finally, we only care about the physical degrees of freedom. So then, final step of the quantum channel is trace out the ancilla degrees of freedom. With all three steps, we have the formal definition of a local quantum channel.
Can I ask a question?
Yes.
Yeah. Here, what is the geometry of the ancilla system? I mean, locality just depend on the geometry of the system.
Well, all the degrees of freedom in the ancilla degrees of freedom should be put in a trivial product state.
I mean that the locality should depend on the spatial manifold. So if you just add some ancilla system, you need to just assign some spatial manifold to this ancilla system. So is this just a copy of the system?
Well, not necessarily a copy of the system. We can add a very large ancilla Hilbert space.
Yeah, but we cannot say that which two qubits are close and which others are long from each other. Yeah.
Well, actually, the second step is critical in the sense that the second step should be a local unitary circuit for the enlarged Hilbert space. Should be local.
Okay, thank you.
Sure.
I think the question is asking, suppose I have a definition of local interaction in the original system. But now when I add ancilla, what's the new definition of the new system? What's the new definition of locality in the new system?
Well, the locality is defined for the enlarged Hilbert space. Well, we put some additional degrees of freedom in the whole system, and then the locality is still there, should be defined in enlarged Hilbert space, and every single gate in the enlarged Hilbert space should still be local in the enlarged Hilbert space.
Yeah. What I mean is that if we want to define the locality, then we should just first put a spatial manifold here, and then we can define what is the local term, what is the neighbor of one terms, one qubits. And for the
example,
system,
if you have a
we should
lattice,
also introduce such kind of geometry to first, then we can define the locality, then we can define the local gate.
yeah. For example, if you have a lattice and there is a qubit on every single side, the ancilla degrees of freedom could be another copy of the lattice, and we put the two copies of the lattice all together very close, and the locality, and such that the corresponding ancilla degrees, local ancilla degrees of freedom and the physical degrees of freedom is very close, and that we can imply a local gate between them, between physical and ancilla.
Okay, thank you.
Yes. Okay. Well, as I said, I told you before, for the pure state, the two-way connectivity is pretty natural in the sense that if you have a one-way connectivity, then two-way connectivity is automatically satisfied because because of the unitarity. But it's not the case for the mixed state. In fact, I'm going to show you a very extreme example that every mixed state is one-way connect to a product state by local channel. Okay, let me first consider a mixed state and put it with an ancilla degrees of freedom. Then we apply local swap gate for every single degrees of freedom, every single pair of degrees of freedom between physical and ancilla. Note that here we are considering the situation that the Hilbert space of physical and ancilla are identical. Then we can apply a local swap gate between system and ancilla. Then we trace out the ancilla. It's following the above steps. We are actually have a local quantum channel that evolve the density matrix to a product state. So if we only require one-way connectivity, it's meaningless to talk about the phase-on matter because every single mixed state is one-way connected to a product state. So if we really want to talk about the phase-on matter, the two-way connectivity is pretty essential. Okay. What do I mean by the two-way connectivity? It means that if we have two density matrices, let's say rho 1 and rho 2, we should find two local channels such that we can deform rho 1 to rho 2 by one of the channel and deform rho 2 to back to rho 1 by another channel. Okay. The channel is not necessarily to be reversible because of the non-unitarity of the quantum channel. Okay. After talk about the equivalence relation of the mixed state, let's talk about the symmetry of quantum states. For pure state, the symmetry is pretty simple in the sense that if we say a pure state psi have a symmetry G, it means that if we apply a symmetry operator, let's say UG on the psi is invariant up to a global phase. And then for mixed state, things become completely different in the sense that there are two classes of symmetries. One is called strong symmetry, which is also called exact symmetry. It means that if we apply a symmetry operator on a specific side of the density matrix, the density matrix is actually invariant up to a global phase. The quantum mechanics tell us the global phase is not that important. The second class of the symmetry is actually the weak symmetry. The weak symmetry, by definition, is that if we only apply the symmetry operator on a specific side of the density matrix, the density matrix is no longer invariant. But if we conjugate the density matrix by the symmetry operator, the density matrix is actually invariant. You may notice that the weak symmetry or average symmetry is a weaker condition than a strong or exact symmetry. Okay. After the background introduction, let me outline my today's talk. There are three main parts of my today's talk. The first part is a gap of mixed state. This part is quite counterintuitive in the sense that, in open quantum system, we cannot even define a concept of Hamiltonian or gap energy. The energy is no longer a good quantum number because of the dissipation. So you may ask me a question: what do you mean by gap for mixed state? Let me show you later. And this part includes the correlation and the relation between the correlation and the mutual information. And for mixed states, I'm going to introduce the concept of conditional mutual information and the Markov length. And after the generalization of gap to the mixed states, I'm gonna show you the gapped mixed state. In particular, the average SPT phases is a typical example of gapped mixed state. And then after discuss the gapped mixed state, let's discuss non-gapped mixed state. And in particular, I'm going to show you the recent developed strong two-way spontaneous symmetry breaking is a typical example of non-gap mixed states. Okay, wonderful. Operators. Let's say OA and OB supported at the regime A and the regime B. You can see the figure in the slides. It's a condensed matter perspective. Well, in 2008, in this seminal paper, there has been proof that if you consider the mutual information between the regime A and the regime B, this sort of mutual information can also capture the correlation behavior of the quantum state. The formal definition of mutual information is actually the SA plus SB minus SAB, and here SA is the von Neumann entropy of the reduced density matrix in the regime A. And in this paper, they rigorously proved that the mutual information serves as an upper bound of the connected two-point correlation function between A and B. Here, OA and OB are local operators supported within A and B, respectively. And another condition for OA and OB that both OA and OB should be, the bounded operator in the sense that the operator norm should be finite. So with this property, we can see that the mutual information serves as an information perspective of the correlation behavior of the quantum states. And we should say that this condition is actually well defined for both pure state or mixed states. Okay?
Question?
Then for pure, yes.
Here, OA and OB are assumed to be Hermitian.
Not necessarily.
Then in the red inequality, the right-hand side may be a complex number.
Well, be Hermitian. I think it should be unitary, not Hermitian.
OA and OB should be unitary?
The unitary would be completely okay. For example, if you consider Pauli degrees of freedom, let's measure the ZZ connected correlation function. The Z here is a unitary operator.
If it's assumed to be unitary, then you don't need to write the operator alone.
Well, it can up to a unitary because a non-unitary, if you have, well, more generally, if you have a non-unitary operator, then it's probably have the form that the operator norm at times a unitary.
So suppose OA and OB are just two generic local operators, then what does this inequality become?
If OA and OB are most generic
local operators, the left-hand side is the real number. The right-hand side, if OA and OB can be non-Hermitian or even unitary, then this C squared may be complex.
I think if you measure the correlation, if the connected correlation function is complex, I think it should be modified to a modulo square.
Okay, thanks.
Okay, wonderful. Thanks for the question. And furthermore, for the pure state, Hastings proved that there are two concepts that are sort of equivalent. The first concept is that a pure state is a ground state of a gapped local Hamiltonian. And the second concept is that this sort of state has a short-range connected correlation function or a finite correlation length. Hastings proof rigorously proves that if a pure state is a ground state of a gapped local Hamiltonian, then all possible connected correlation functions should be exponentially small. Equivalently, the correlation length is finite. And so does the mutual information, because the mutual information is actually a information perspective of the correlation behavior. Okay, after talk about the pure state, let's introduce another correlation behavior that is called conditional mutual information. You can imagine. Let me show you the conditional mutual information. Let's consider the tripartition of the system with the geometry as illustrated in these slides. We have a finite regime A, a buffer regime B with a finite width WB, and the C is the entire remaining system. And the CMI is defined as the SAB plus SBC and S minus SB and minus SBABC. Here S is again the von Neumann entropy. You may wonder why I didn't introduce the conditional mutual information for pure state, because if rho is a pure state, then the CMI is actually equivalent to mutual information. You can very easily to verify that, because for pure state, first of all, SABC equals to 0. Then SAB equals to SC, SBC equals to SA, and SB equals to SAC. Then for pure state, the CMI equals to MI. But for mixed state, it's not necessarily the case, because first of all, SABC is not necessarily to be 0. So for mixed state, we can other than the correlation length, because the inequality between the CMI and MI, we can further define another length scale from the short-range CMI that is called Markov length. If the CMI between A and C conditioned by B, then we can define a Markov length to capture the exponentially small conditional mutual information. Well, by the way, the physics behind the conditional mutual information is that the correlation between A and C that is not intermediate by the regime B. It's some sort of global correlation. And from the fact that the CMI is not necessarily equals to MI for the mixed state, there might be some very subtle global correlation for mixed state. I'm going to show you a representative example of such sort of global correlation at the last part of my today's talk. Well, the Markov length is really pioneered by Shengqi Sang and Tim Shea last year. It's very exciting progress for mixed states. Okay, after introduce the mutual information and the conditional mutual information, actually we're ready to define the gap for mixed state. You may ask me a question that we don't have a Hamiltonian, we don't have a energy as a good quantum number for mixed states, but let's recall the pure state. For pure state, because of Hastings' result and the mutual information, we can sort of think that the mutual information and the corresponding correlation length is some sort of information perspective of the gap of the local Hamiltonian for pure state. As an analog, let me define the concept of gap for mixed state in the information perspective. Let's say if rho is a mixed state with a short-range mutual information and the short-range conditional mutual information, then we say the corresponding density matrix is a gapped mixed state. In other words, for a gapped mixed state, both correlation length and Markov length should be finite. That's the information perspective and the corresponding generalization of the gap of mixed states. Okay, wonderful.
Can you give some example where only one of them is finite and the other is infinite?
Well, very interesting question. I'm going to show you at the last part of my talk. I can tell you the answer. The strong-Twig symmetry breaking is a typical example of what you ask.
In that case, per
In
se,
that case, the mutual information is exponentially small, but the conditional mutual information is finite.
I see.
Yeah, that's a very interesting example. Thanks for your question. Okay, after the formal generalization of the gapped mixed state from the quantum information perspective, let's discuss the gapped mixed state. Okay, before we talk about the gapped mixed state, let's recall one of the most representative example of gapped pure state that is called SPT phases. You know, for a formal definition, the SPT phases should be a gapped unique ground state of local Hamiltonian with short-range entanglement. And the SPT phases are non-trivial if and only if the protecting symmetry are unbroken. In other words, if we don't care about the symmetry of the system, the SPT phases should be adiabatically connected to a product state. There are several representative examples for pure state SPTs, including the 1D Haldane chain and the 3D free fermion topological insulators, etc. Okay, let's recall a very simple example of 1D SPT, that is 1D cluster state. We have a local Hilbert space that for every single side there is a qubit, and we have odd sides and even sides. The Hamiltonian, the parent Hamiltonian of cluster state is a product of ZXZ on nearest neighbor 3 sides. Here, Z is a poly Z operator and X is a poly X operator. There are Z2 cross Z2 symmetry for cluster state. The one Z2 is defined as the product of X on all even sides, and another Z2 symmetry is actually the product of X of all odd sides. The ground state of these cluster Hamiltonian is pretty easy to be prepared from a product state by a control Z circuit. Here, the control Z circuit is composed of a local control Z gate for every pair of qubits. There is a very typical structure of the 1D cluster state that is called the Decorate domain wall state. As I illustrated in the figure of these slides, if we consider the degrees of freedom on all sides along the Z direction, let's say, we should put a plus of X if there is no domain wall between 2 nearest neighbor odd sides. Let's say, as we say, the blue plus here. But if there is a domain wall between 2 nearest neighbor odd sides, for the even side in between them, we should put a minus X. That's a Decorate domain wall picture of the 1D cluster state. Okay, a very typical property of SPT wave function is a symmetry localization, in the sense that when we consider symmetry, we truncate the symmetry operator in a finite regime and apply the corresponding truncated symmetry operator to the SPT wave function. We conclude that the application of truncated symmetry operator can only have non-trivial effect on the truncation boundary. All other parts of the system should be invariant. For example, for cluster state, if we truncate the even symmetry between 2M and 2N, then the effect of the application of this truncated symmetry operator is equivalent to 2 poly Z operators located at 2M minus 1 and 2M plus 1. That is the physical origin of the long-range string order parameter of the 1D SPT phases. Okay, and for most generic symmetry localization of SPT proposed by the Els-Nayak, it means that if we have a generic SPT in arbitrary dimension and we truncate the system, we truncate the symmetry operator in a finite connected regime, then the application of the truncated symmetry operator can only have some non-trivial change on the boundary of your truncation, and all the other places should be invariant in arbitrary dimension. That is the Els-Nayak symmetry localization. That's the key property of the SPT. So what about this? Yes.
Yeah, I have one more question. So people often say we can use string order parameter to detect one-dimensional SPTs.
Yeah.
From the perspective of the topological quantum field theory of the SPTs, why should this work? what does this string of order parameter mean in the TQFT?
Well, quite frankly, I don't know from the perspective of TQFT. But what I said is, I just may I ask you a question? Is there any implication of the symmetry localization in the TQFT perspective? I don't know.
I think one can figure it out by asking whether there's any anomalous theory when the theory is on boundary.
Oh, I think you are right. Yeah. I think you are right. If you consider a truncated symmetry operator, you are actually think your truncation boundary as sort of a physical boundary of your system. Am I right?
Maybe, I don't know.
Yeah. I'm sorry, I don't know the TQFT perspective of the string order parameter, but I do know the physical origin of the string order parameter from the perspective of symmetry localization.
Okay, thank you.
Okay. Yeah. Yeah. After talk about the symmetry localization of pure state SPT, what about the mixed state? First of all, as I told you at the very beginning of my talk, for the mixed state, we have two sort of symmetries, including strong symmetries and weak symmetries. So let's discuss the symmetry localization of them separately. For the weak symmetry first, we have a theorem that for a gapped mixed state, let's see again the tripartition of the system with A, B, C regimes. And for a gapped mixed state, a weak symmetry G can always be effectively localized in the sense that if we truncate the weak symmetry operator to a regime A, let's say the truncated symmetry operator WA, and then we conjugate the density matrix by WA, the effect of this truncated weak symmetry operator is equivalent to a local quantum channel supported on the buffer regime of B with a finite width of the system, of the finite width. Then we proved that the local quantum channel is only supported on B, so we proved that the weak symmetry is actually localized for the gapped mixed state. Okay, then for the strong symmetry localization, before I talk about the strong symmetry localization, we should introduce another constraint to the mixed state that is called symmetrically invertible mixed state. The symmetrically invertible mixed state means that if rho is symmetrically invertible, then there exists another strongly symmetric density matrix, let's say rho total, such that rho tensor rho total is two-way connected to a product state by two strongly symmetric local quantum channels. Well, this concept is pretty close to the pure state SPT because the SPT phases is invertible state in the sense that if for a SPT state psi, we can always find another pure state psi total such that psi tensor psi total can be evolved to a product state by symmetric local unitary operator. That is quite as an analog. And after defining the symmetrically invertible mixed state, we actually have the condition of the strong symmetry localization. For a symmetrically invertible mixed state, a strong symmetry can always be effectively localized. And you can see that if you truncate the strong symmetry operator A, little a, to a finite regime, the capital A, then apply the truncated symmetry operator, then which is equivalent to applying an operator VB on the rho. Here VB is only supported on the buffer regime B. Okay. Then after talk about the strong and the weak localization, I'm going to show you that the average SPT, which is also called mixed state SPT, is actually the gapped symmetrically invertible mixed state.
Sorry.
Yes.
Here when you say local, do you mean strictly local or quasi-local?
Here is strictly local. Yeah. We
Then
prove that it's strictly local.
isn't that a bit surprising?
Uh-huh.
I think that's a bit surprising.
Well, Yeah, let me heuristically demonstrate this local is that the proof of the theorem of this weak symmetry localization is the heuristic understanding of this proof is sort of let's trace out the buffer region B and perform the path recovery of B. And then the trace out and the path recovery compose them all together is a local channel supported of the buffer region B.
Strictly local.
That is local.
Okay.
Yes. Okay. And as an analog of pure state SPT, which is a symmetrically invertible pure state, I'm going to show you that the average SPT is a gapped symmetrically invertible mixed state because, well, it's a heuristic understanding of this fact is that, from the invertible condition of the pure state, we can actually prove the local symmetry localization. Then for mixed state, if you as an analog, you want both strong and weak symmetries to be localized, then the condition of the localization of strong and weak symmetry are actually the symmetrically invertible and the gapped respectively. So that's why I say the average SPT is some sort of gapped in symmetrically invertible mixed states. Okay, let me show you a very simple example of the ASPT state, that is a cluster state under decoherence. Let's consider a cluster state, pure state at the beginning, and apply a single Z defacing channel on all even sides. Sorry, and you can see that from the explicit form of the cross operator, the odd Z2 symmetry gonna be broken to a weak symmetry because the cross operator is not commute with the even Z2 symmetry. So right now, after applying this sort of channel, you can see that K symmetry is still a strong symmetry, but G is a weak symmetry. In particular, if P equals 1/2, that is a strong measurement. The corresponding density matrix is actually the product of projection operator of the ZXZ centered at odd sides. And even the ZXZ stabilizer centered at even side were broken by the local channel. We can still, for this sort of density matrix, we can still define string water parameter, which is long range. So that's why I still tell you it's a non-trivial ASPT state. And okay, as I told you before, there is a very elegant feature of the pure state SPT, which is called decorated domain wall in the example of 1+1D cluster state. And then we initialize by that example, I'm going to show you a symmetry localization. Okay, for the most generic case, the decorated domain wall construction of a pure state SPT is that if we consider a system with a K symmetry and a G symmetry, and if you want to establish a G-symmetric wave function, one way to consider that sort of property is that we consider all possible G-symmetry breaking patterns. And then we perform the quantum superposition of all of them. And if we can achieve that, please notice my phrase here, if we can achieve that, I'm going to show you that this sort of quantum superposition is not always be achieved. But suppose we can do this, then the obtaining single wave function is G-symmetric because this sort of wave function is a quantum superposition of all G-symmetry breaking patterns. That's why this wave function is symmetric of G. And we have another symmetry K, then we can consider the decoration of K symmetric degrees of freedom on the defects of G symmetry. For example, let's consider a 2D system. We can decorate a 1D K symmetric invertible states on the orange strips and a non-trivial K charge on the green dots. And you may notice my phrase before that the quantum superposition of all G symmetry breaking patterns, if we can achieve that, yeah, indeed, if we really want to get a gapped invertible pure state, by the symmetry, by such sort of quantum superposition of the G symmetry breaking pattern, let's say it's a G symmetry proliferation, there should be some consistency conditions. First of all, the first condition is that all the decorated defects should be fully gapped. Otherwise, you're going to have a gapless ground state of some gapless Hamiltonian. That's not the thing we want. The second consistency condition is that for all possible G symmetry breaking patterns decorated by K symmetric degrees of freedom, they should share the same K charge. Otherwise, the quantum superposed state is so-called K-symmetric state without a well-defined K charge. It's not unphysical at all. So that's the second consistency condition of the G-symmetry proliferation. The third is that we are actually considering a quantum superposition. You know, for the quantum superposition, the relative phase between different relative phases between the different patterns where quantum superpose are really important. In particular, if we consider a closed path of the deformation of G symmetry breaking pattern, let's say if we consider such sort of defects, move to this, and go around a very long circle and back to the original form, the accumulated Berry phase all along the path should be vanished. Otherwise, you're going to have a multi-value wave function, which is unphysical at all. So that's the physical origin of the third consistency condition, is that the consistency of the relative phase of different G symmetry breaking patterns. That is quite complex and complicated. Okay, after the review of decorated domain wall of the pure states, a pure state SPT construction, let's consider the average SPT. Let me notice that here K is a strong symmetry and G is a weak symmetry. Okay, again, we completely break this G symmetry with plenty of G symmetry breaking patterns. Okay, and then we decorate some sort of K symmetric gapped symmetrically invertible mixed states. Okay, right now we have almost identical ingredients for ASPT with the SPT. The ingredients are almost identical. And then let's see the proliferation of G symmetry. You should notice that the G symmetry proliferation here is just a weak proliferation towards a weak symmetry, not a strong symmetry. Okay, let's consider the very subtle difference between the two situations. First of all the defects decorated by K degrees of freedom should be K symmetric, gapped, strongly symmetric. Let me notice, gapped symmetrically invertible mixed states. That's the first consistency condition. It's pretty much similar to the previous condition of the fully gapped K symmetric states. Pretty much similar. And the second condition is that for all the G symmetry breaking patterns of the G symmetry, we should require them to have the same K charge, because we really want to have a density matrix with a strong K symmetry. When we say a density matrix has a strong symmetry, you should still have a well-defined charge of the strong symmetry K. So the second condition is also pretty much similar to the pure state situation, but nevertheless, the key difference between the pure state and mixed state is a third one. We should notice that right now we just want to achieve a weak G symmetry. Then the G symmetry proliferation is just a classical proliferation. We no longer have to do a quantum superposition. The things we're gonna do is just put all the G symmetry breaking patterns to a ensemble of states. That's some sort of classical superposition. So then we consider, when we consider a ensemble of states, there's no relative phase between different states within this ensemble. So there's no relative phase, then accordingly, we no longer have such sort of Berry phase inconsistency for the ASPT states. So you may conclude that the decorated domain wall construction of both pure state SPT and ASPT are almost identical. We have almost identical ingredients, but less constraint for ASPT than the SPT. So you may ask a question: you have almost identical ingredients, but less constraints. Is there any emergent states that are only well defined for open quantum system? Indeed, yeah. Let me show you a very simple example of intrinsic ASPT. Let's consider a Z4 symmetry that is could be treated as a non-trivial extension between two Z2 symmetries in 1D system. From the group cohomology classification, we can see that there's no pure state SPT because of H upper 2 Z4 U1 is actually Z1. And let's consider a local Hilbert space that we put a single qubit on a site and another single qubit on each bound. And the Z4 symmetry generator as formulated here, but as UG and UK, such that UG squared equals to UK and UK squared equals to 1. So far, everything is pretty good. There's nothing awful. We have a local Hilbert space, we have a symmetry, but if we really want to have some sort of SPT pattern, we should impose some projection operator to impose the Decker domain picture of ZXZ to the local Hilbert space. Nevertheless, some subtle thing gonna happen if we impose such sort of Decker domain projection. Let me show you that in the projected subspace, the UG symmetry operator is projected to a non-local symmetry operator. You can see that for different pieces of this symmetry, you can see that different pieces of the symmetry operator are no longer commute, and UK equals to 1. And for the audience who are familiar with SPT, this sort of symmetry operator is exactly the boundary anomalous Z2 symmetry of 2 plus 1D Levengood state. What I'm showing to you is that in the projected subspace, there is some projected anomaly. If you really want to impose the Decker domain wall, that's why we do not have any pure state SPT for the symmetry class of Z4 in one-dimensional system. Thanks to the Thorngren Vishwanath and Ruben Vereisen, they propose a concept of gapless SPT for this sort of situation. For this example of Z4 symmetry, the gapless SPT is composed of 2 ingredients. The first ingredient is a Decker domain wall pattern imposed by the projection operator, and the second part is the gapless CFT at the anomalous boundary mode of 2 plus 1D Levengood state. The purpose of introducing such a gapless mode is to compensate the anomaly introduced by the projection operator. That's the physical intuition of the gapless SPT. Then let's back to the situation of mixed states. Right now, for the mixed state, we only require the UG symmetry to be a weak symmetry. Then we can safely add some decoherence channel, let's say epsilon and n, to destroy the UG symmetry to weak symmetry. And we can prove that under these sort of decoherence channels, all the algebraic correlation from the Levengood boundary has been completely destroyed by this sort of decoherence. So we can conclude that let's start from a Z4 gapless SPT and apply some decoherence. We can actually propose the Z4 intrinsic average SPT. Okay. That's the typical and simple example of intrinsic average SPT phases. Good. After the introduction of the gapped mixed state and the average SPT, let's move to the last part, which is called non-gapped mixed state. Let's keep Liu Jun's question about the correlation length and Markov length. Is there any situation that only one of them is infinite, the other should be finite? Let's keep the question in mind. Okay, Before I talk about the mixed state, let's recall the pure state spontaneous symmetry breaking as the one of the most important organizing principle in condensed matter physics. Let's consider 1D chain. And let's consider the Cass state, which is a quantum superposition of all up, down, all down. There are several. I think everybody knows that this state is sort of a spontaneous symmetry breaking of Z2 symmetry, and there are some sort of key properties of this Cass state. First of all, is the Cass state has a very long range ZZ correlation function, and the other thing is that the Cass state is non-invertible in the sense that we can never find another pure state, let's say psi total, and a strongly symmetric unitary operator such that we can deform psi tensor psi total to a product state by U. It's not possible at all. Okay, thanks to the Ginsburg-Landau paradigm, a large class of phase matter can be classified by the patterns of this SSB, including the classical Ginsburg-Landau that describe the SSB from a weak symmetry to nothing, and the quantum Ginsburg-Landau that describe this SSB from the strong symmetry to nothing. So the only remaining open question is new possible strong SSB for mixed state that breaks the strong symmetry to weak symmetry. Okay, let's consider the 1D Ising chain again with a strong Z2 symmetry. Let's consider such sort of density matrix which is proportional to the 1 plus product of X. This state is literally the maximally mixed state within the even charge sector. It means that every single state within the ensemble should have an even charge of the Z2 symmetry. This state is pretty easy to be prepared by a depth 1 local channel as I formulated in this slice. And you may notice that the ZZ 2-point correlation function of this sort of density matrix is 0. So you may ask me a question. There's no SSB at all. Why you should consider such a trivial state? Okay, let me show you the reason. Let's recall the Cass state again. As I said before, the Cass state has a very long-range ZZ correlation functions. We can heuristically understand this sort of long-range ZZ correlation function by 2 steps. Let's start from a Cass state and apply a poly Z operator to Cass state. Then the obtained state, let's say Zi psi, is orthogonal to the previous one. That's pretty straightforward. Nevertheless, if we further apply a Zj operator on the intermediate state, you can see that Zj psi is back to the original form, no matter how far I and j are separated. That's the physical intuition of the long-range correlation of the poly Z operators. As an analog, for the density matrix I told you before, that is 1 plus x, although the 2-point correlator of the poly Z operator is short-ranged, let's consider the conjugation of the poly Z operator rather than apply a poly Z on a specific site. Let's first conjugate the poly Z operator at I, and then the density matrix rho and the Zi rho Zi are actually orthogonal in the sense that the fidelity between them is 0. And if we further conjugate another poly Z, let's say Zj, to the intermediate state, the obtained density matrix are identical to the previous one, which is reflected by the fidelity between them is actually equals to 1, which emphasizes that these 2 density matrices are identical. Let's call the fidelity between rho and the ZZ rho ZZ are actually the fidelity correlator of the poly Z operator. Okay, and the example I showed you before has a short-range 2-point correlator, but a long-range fidelity correlator. Inspired by this example, we actually have a more generic definition of the fidelity correlator as an order parameter of the strong to weak symmetry breaking, in the sense that if a mixed state with a strong symmetry G has a strong to weak SSB, if the following fidelity correlator is of the order 1, it's long range. Here, OX and OY are local charged operator of the strong symmetry G supported around X and Y respectively. Okay, You may ask me a couple questions. First question is that, oh, you define your mathematical correlation function, but when you talk about the phase of matter, you should discuss the universality of the corresponding phase. Otherwise, you can only claim you find a phenomenon rather than universal phase of matter. That's the first question. The second question is that even if you can prove the universality of your correlation function as you claimed as a local order parameter, then why should I call it a spontaneous symmetry breaking? I didn't see anything about the spontaneous symmetry breaking here so far. Where can you capture the spontaneity of the things you are talking about? Okay, let's keep the two questions in mind. First of all, let's recall the stability of pure state SPT. Let's recall the cast state over and over again. The stability of cast state is that if we consider a strongly symmetric unitary operator, then we apply the U to psi, then the final state is also Z to SSB state. As an analog, the stability of the strong to weak SSB is that if we have a density matrix which is a strong to weak symmetry breaking of some sort of strong G symmetry with a long range fidelity correlator, and then we have a strongly symmetric finite depth local quantum channel epsilon. If we evolve the density matrix by the external perturbation epsilon, then the final state epsilon rho also has the strong to weak SSB in the sense of a long range fidelity correlator. With the stability theorem, we can unambiguously claim that the strong to weak SSB is a universal phase of mixed state phase of matter. Okay, then let's talk about the spontaneity of SSB. Let's recall the spontaneity of pure state SSB by review the cast state over and over again. You can see the cast state is as a quantum superposition of all up to all down. This state seems like a symmetric state, but this symmetry property is pretty fragile in the sense that if we apply an infinitesimal Zeeman field along the Z direction on only one side is enough, then the cast state could be immediately collapsed to either all up or all down, depends on the sign of the external edge. So we can that is the spontaneity of the pure state SSB in the sense that a local perturbation can lead to global change of the whole system, and in principle, the global change of the whole system can never be recovered by any other local operation. So as an analog, let's recall the 1 plus x over and over again. Let's start from 1 plus x in the thermodynamic limit, and then we trace out a single qubit. Just one is enough, even in the thermodynamic limit. It's literally a perturbation. We can find that immediately the final state is just a maximum mixed state without a charge sector fixing. Equivalently speaking, this sort of perturbation explicitly destroy the global charge conservation properties, which is a global properties. Inspired by both examples, we actually have a theorem of spontaneity of the strong to weak symmetry breaking, in the sense that if rho has a strong to weak SSB, then we can always find a local symmetry breaking channel epsilon I, which is supported around I. Then we can never find another local channel which is also supported from around I, let's say rho tilde, such that the epsilon tilde can recover the effects of the epsilon I. It emphasized that a local channel can never be recovered by any other local channel. It means that the local channel leads to global change of the whole system. Okay, finally, let me address Liu Jun's question. If the corollary of the spontaneity theorem is that if the rho has a strong to weak symmetry breaking, then the conditional mutual information with the tripartition with the geometry I illustrated in these slides over and over again is long range, which is equivalent to a divergent Markov length. But by the example of 1 plus x, you can easily to justify that the mutual information is 0. That's a typical example that we have a state with a finite correlation length, but of infinite Markov length. Okay, let me summarize my today's talk. today I talked about the generalization of gap to the mixed quantum states, and then I talked about the gapped mixed states, including the average SPT as a typical example. And lastly, we talk about the non-gapped mixed state, including the strong to weak symmetry breaking. Okay. Here's my today's talk. Thanks for your attention.
Okay, thank you, Jian-Hao, for the interesting talk. Any other questions?
Hi. Is there
Yes.
any way that we can relate the gapness here for the mixed state to, similar ways as the pure state for the Hamiltonian? I mean, we can just construct some Lindeblad operator or some.
Well, that's a very interesting question, but I think it's still open question. I think it's still open question. It's a really interesting if you can find some relationship of the gapped mixed state from their parental Lambda such that the density matrix you are talking about as a steady state. I believe that's your question, right?
Yeah, yeah.
But I believe it's still an open question.
Oh, okay. Okay.
Thanks for your very interesting question.
I think this question, even for pure states and Hamiltonians, it has not been answered.
Well, I think it's one way because Hastings shows that if a pure state is a gapped ground state of a local gapped Hamiltonian, then the correlation is sort of short range.
Oh, sorry. I was talking about something else.
Oh.
This one I know, and also one can show that. Yeah, I was talking about something else. I was talking about if I only know that I obtain a state by a finite type evolution generated by local Hamiltonian from a product state, then it's not whether this state can be a ground state of any local Hamiltonian.
Yeah, I agree with you. It's still an open question, even for pure state. Yes.
Other questions? Okay, if not, let's thank Jian-Hao again. Thank you.
Thank you, Liu Jun.
Yeah, and we can leave now. Bye.
Yeah, sure. Have a good day, guys.
Bye.